Okay, let's get started today. So we're just going to be doing exam review. So I'm just going to be taking problems from the review I posted last week. And then I recorded, right? Yeah, I'm going to take problems from the review I posted last week and just go through them. So there's two classes I have for Calc 3. So my first class is from 12 to 12:50. So I've already gone through some of the problems. All the problems I have circled in green are problems I've already covered. They're mostly on the integral section. And so I'll send you a video lecture of those problems that I did in my previous class, as well as the problems I'm going to be going over in this class. So you'll have two videos to reference when going through the exam. Let's see. Yeah, so I think like the harder part of the exam is going to be chapter 15. Chapter 14 is mostly just like gradients and directional derivatives, and then there'll probably be a problem on optimization. Aside from that, most of it's going to be like the harder parts are going to be in chapter 15. One thing about the chapter 14 problems is there was one typo. It doesn't really, I mean, it changes things, but it doesn't really make things that much more difficult or anything. Actually, I didn't work through this. I don't even know if that's true or not. But for problem 6, it says it's x to the y power. Instead of doing x to the y power, just do x squared. Right? I didn't intend for the derivative to be annoying to compute or anything like that. It was supposed to be x squared, and I just did a typo. So it should be x squared instead of x to the y power. So I'll make things easier for you. And then I think everything else should be fine on the review. And so I just chose problems on my previous class. But before I just start choosing problems, are there specific problems that people want me to go over? I don't know if people have it in front of them or not, but I think any problems in particular? Okay, so I'll go through, I think problem 15 is one of the harder problems from the review. So I'll go through problem 15. It'll be a good idea for me to explain what's going on verbally. So this is a problem where it just asks you to set up the integral, but don't compute this integral over d, where d is kind of like this crescent moon, right? It's this region right here. And so just by looking at this, it's similar to a problem we've done in the past, where you want to split up the integral into two other integrals, because we kind of have this circle of radius 2 right here. And it's kind of easy to write out an integral of radius 2 or a circle of radius 2 using polar coordinates, right? That's just going to be r goes from 0 to 2, and then theta goes from 0 to 2 pi. What's a little bit more difficult is taking into account the circle that we have here in terms of polar coordinates. So that's kind of the hint I give you, right? So to find the polar representation of the circle of radius 1, centered at 1, 0, which is what we have here, it tells you to use the equation of that exact circle, right? So the circle of radius 1 centered at 1, 0 is given by the following. So we want to manipulate this in order to determine what our bounds for r and, well, really what r is going to be. Actually, r and theta. The bounds for theta is actually a little bit unique in this as well, right? So this is our region D here. And so we're going to write D as being the difference between two other regions. So it's going to be this D2 minus D1, where D2 is the circle of radius 2 centered at the origin. And then D1 is the circle of radius 1 centered at the point 1, 0. Okay, and then if you want to do the integral over d, it suffices to do the difference of the integrals over these two regions. Right, so I'll write down kind of this information over again. So this is problem 15. Okay, and so we're looking at this integral over d, and we have x squared plus y squared. And then I guess the other important aspect is the picture itself. Right, so we have a circle of radius 2, and then we're removing the circle of radius 1. So it looks something like this. It's not perfect, but it's not even close to being perfect, but it's good enough. Okay, so this is kind of what we're looking at, right? So the easier part is just writing the integral out over d2, where d2 is a circle of radius 2. So with d2, we have the following bounds of, or D1, sorry. No, it was D2. I don't know why I wrote it in that order, but it was D2. Okay, so this is, we're interested in R. Oh, that's the eraser. We're interested in R and theta. So if this is the circle of radius 2, you don't have to be clever to determine the bounds. So this is going to go from 0 to 2. And then theta is going to go from 0 to 2 pi. Right, so D2 is just the circle of radius 2. And so that means the integral over D2 of the square root of x squared plus y squared dx dy. This is just going to be equal to the following double integral. So we're going from 0 to 2, 0 to 2 pi. The square root of x squared plus y squared is just equal to r in polar coordinates by the distance equation. So this is just the distance from the point xy to the origin 0, which is really just the radius. And then you have r dr d theta. So you really have an r squared once you multiply the r's together. Okay, so this is the first part of the setup. We have the integral over this circle of radius 2. And now we need to omit this circle of radius 1 centered at the point 1, 0. Right? And so now we have this point, or we have this other circle, D1. So what's going on with D1 is the following. So to account for D1, we use the formula that I gave you in the hint. So we know a circle of radius 1 centered at 1, 0 is given by the following equation. So we have x minus 1 squared plus y squared is equal to 1. And so you can write everything out. Well, we can expand all the terms out to get the following. So this is going to end up being x squared minus 2x plus 1 plus y squared is equal to 1. And then we want to manipulate this equation, right? So we have a plus 1 here, and we have an equals 1 here. So you can subtract 1 from both sides. So this would give us x squared minus 2x plus y squared is equal to 0. And now we can write everything out in terms of r and theta, right? We know x is equal to r cosine theta, and we know y is equal to r sine theta. So this is the same thing as having r squared cosine squared theta minus 2r cosine theta. I want to move this down because I need more space. And then this is going to be plus r squared sine squared theta. And then this is all equal to 0. And so what we want to accomplish is we want to be able to find an equation for r in terms of theta in order to determine what the upper bound is going to be. And that'll be the description of the circle itself once we determine what the upper bound is. And so there's a couple of things we can do here to make life easier for us, right? We have an r squared times cosine squared theta plus r squared times sine squared theta. So if you factor out an r squared, you get r squared times cosine squared plus sine squared, which would just give you r squared, right? So this is the same thing as just having r squared minus 2r cosine theta is equal to 0. And then we can add r, like 2r cosine theta to both sides to get r squared is equal to 2r cosine theta. And then from here, if you divide both sides by r, which we can do because our circle is radius 1 and not 0, this is equal to 2 cosine theta. So this is going to serve as the upper bound for what our r is going to be. So we have r ends up being equal to 2 cosine theta. That's the description of our radius, right? And so this tells us that we have that 0 is less than or equal to r, which is going to be less than or equal to 2 cosine theta. And then we also need to be able to determine what theta is going to be. And so to determine what theta is going to be, you kind of want to combine what you see here for r with the picture that we have drawn. I mean, it's probably better to look at this picture, right? So there's 2 points where we're going to have r is equal to 0, or where we intersect this point right here. And so it's just a matter of finding like where we're going to have these two intersections. Like we start here, you go around, and then you end up here once more. And there's multiple answers you can have for this actually. But 2 points that are going to end up working are going to be theta is equal to minus pi over 2, and then theta is equal to pi over 2. So if theta is at minus pi over 2, you start here. And then as theta increases, you go around the circle until eventually you hit pi over 2 again, or you hit pi over 2 and then you hit the same point over again. Right, so 2 points that end up working for theta are going to be pi over 2 and then minus pi over 2. And again, there's multiple answers you can have here. You can shift around theta, or you can shift around these values because it's periodic, and those values would work as well. But these are instances of just two values that would end up working. And so the hard part of this is over, right? We determined the bounds for r, and we determined the bounds for theta as well. And so the integral over d1 is going to look like the following. So this is the integral over d1. This is the original integral in terms of rectangular coordinates. So this is like dx, dy. If we rewrote things in terms of polar coordinates, it will look like the following. So we have r is bounded between 0 and 2 cosine theta. And then we have that theta is bounded between minus pi over 2 and then pi over 2. And then the inside of the integral doesn't change from what we did before, right? It's still just going to be r squared dr d theta. And so putting these two things together to get a final answer, we have the following. So this integral over d of x squared plus y squared dx dy. This is equal to the first integral we had written out. So this is over the circle of radius 2. And then this is r squared dr d theta. And then this is going to be minus the integral that we just found. So this is going to be minus the integral from 0 to 2 cosine theta, and then minus pi over 2 to pi over 2. And then this is also r squared dr d theta. So this is how you would set up the integral. And then I don't ask you to compute the integral itself. I just ask you to set it up. And so this would be the answer for this problem. So I think this is probably the hardest problem from the exam review. At least setting up the integral for D1 is a little bit different from what we've done before. So I'm probably not going to ask something like this on the exam. At least it's not going to be exactly like this, because I think finding theta is like a little bit unintuitive. But if you can understand how to do this problem, you'll know how to do the polar exam problem, or polar equation problem on the exam as the takeaway. Any questions about 15? Yeah. Yeah, it's really just a matter of looking at the picture. And again, you can shift bounds. Like there's multiple answers you can have for the bounds of theta, but the big idea is we know that r, like what we ended up finding was that r is equal to 2 cosine theta. So what we need to do, like if we start here, like what I'm doing in red, if we start here, this corresponds to when r is equal to 0. And then we want to find another point such that when we complete the circle, r is going to be equal to 0 again. And so we know cosine is equal to 0 at minus pi over 2. And we also know it's equal to 0 at pi over 2. So I just chose those two values. You can also do like theta is equal to pi over 2 as the lower bound, and then theta is equal to 3 pi over 2 if you wanted to. But it's just a matter of choosing two values where like it's going to be equal to 0. You go over a certain amount of intervals until r is equal to 0 again. So you can like always just add pi and find a new interval pretty much. But that's the thinking behind it. Any other questions about 15? Yeah.
If the circle was moved over to the other side, how would you set the bounds for that?
Yeah, I mean, what would end up happening if you move it to the other side, you'll just have to manipulate this equation. So instead, this would be like x plus 1, and then this would be plus y squared. And I guess that would have the effect of having, the only thing that would really change is going to be like the plus 2x here. So this will be like plus 2r. Oh, I guess maybe it would make things.
Would the balance change?
I don't think it would change. Probably not with respect to theta. I mean, I guess it has the effect of multiplication by -1 is what it seems like it would end up doing. Is what it seems like would end up happening, but I can't see it exactly off the top of my head right now. I mean, you can go through the process and just change this to like a +1. I imagine some things would change, but for the most part, it's going to be pretty similar to what we just did. Like you can rely on this process of writing out the equation and then converting it to polar coordinates. Okay, any other questions? Okay. Yeah, so the other two integral, like the other two problems I think are harder from the review are problems 14 and then maybe 16 as well. I covered those in the previous class, so you'll have a video that you can watch where I go through that explanation if you want to see that. The other problems I think are okay for the most part. Is there a particular problem people want me to go through before I just choose another one? Okay, question. 5? Oh, I did 5 in the other class. I forgot to circle that one. I can briefly go through 5 because maybe you don't want to see the long-winded explanation. So for problem 5, this is something you'll have to do on the exam. Like, you have to know how to do the directional derivatives. There'll be a problem where you have to do that. To find the directional derivative, what you really just need to do is like, it'll give you a function. You need to find the gradient of that function. And then you need to do the dot product of that gradient with the unit vector that points in the direction of the vector v. Right, so what you need to find, again, I did this in my previous class, so I'm not going to go full detail here, but you need to find the following. You do the gradient of f evaluated at the point 0, 0, 0, and then you dot it with the unit vector in the direction of v. So you dot it with e subscript v. And so I'll give you like the spoiler. If you do the gradient of f and evaluate it at the point 0, 0, 0, it ends up giving you the vector 0, 0, 1. And then v, this vector v, writing it in, like it's right now written in terms of the standard basis vectors. This is the same thing as the vector 1, 0, 1. So the unit vector that goes in the direction of v is going to be the vector 1, 0, 1, except you divide by the magnitude, which is going to be the square root of 2. And so if you perform this dot product, it's really just a matter of doing 1 times 1 over the square root of 2. So it ends up being equal to 1 over the square root of 2. So there's a more detailed explanation in the video that I'll post after class today for my other class or from my other class. But this is what the answer ends up being. Right. It's just a matter of making sure you know how to compute the gradient and plug in the points to see it ends up being 0, 0, 1. Okay. Any other questions about 5? Okay. Any other questions before I just choose one? Yeah, Hannah. 7? Yeah, 7 is a chain rule problem. So what we're supposing is we have a point P that in terms of spherical coordinates is given by rho is equal to 2, theta is equal to pi over 4, and then phi is equal to pi over 4 again. And so what it wants you to do is it wants you to calculate the partial derivative of f with respect to phi. And it doesn't tell us anything about f, but it does tell us that f partial x at p is equal to 4, f partial y at p is equal to -3, and then f partial z at p ends up being equal to 8. Let me scroll down so I need to make sure I remember what I'm writing out here. Okay, so this is problem 7. I'm going to need more space for this. So for 7, we're looking at the point P is equal to 2 pi over 4 pi over 4 in terms of spherical coordinates. And then I'm just writing down the conditions that I just said out loud. So this is equal to 4. This is equal to -3. And then this component or this part is going to be equal to 8. And so what we want to find is we want to find the following. So it wants you to find the partial derivative of f with respect to phi evaluated at this point p. And so you want to use the chain rule here, right? And so just as a reminder, this is something you should have written on your note card. If we're working over spherical coordinates, we have x is equal to rho cosine theta sine phi. We have y is equal to rho sine theta sine phi. Sorry, I said theta and wrote down phi. I mean, it wouldn't make a difference how I wrote it. But then we have z is equal to rho cosine phi. So these are spherical coordinates. You should make sure you have these on your note card, or you should have them memorized for the exam. And so if we want to find this partial derivative of f with respect to phi, we have the following. So we use the chain rule. So the partial derivative of f with respect to phi, this is going to be equal to the partial of f with respect to x multiplied by the partial of x with respect to phi. And then that's going to be plus the partial of f with respect to y multiplied by the partial of y with respect to phi. And then this is going to be plus the partial of f with respect to z times the partial of z with respect to phi. Right, and so this is why it gives you all these various conditions, right? And so before I continue, we wanted to evaluate at a specific point, right? It wanted us to evaluate at the point 2 pi over 4 pi over 4. And so I'll say we're evaluating at this point 2 pi over 4. I'm running out of space. Pi over 4. Right, and so it's just a matter of plugging in the information that we have now, right? So, I mean, I have it written in Leibniz notation, but like this partial of f with respect to x, this is exactly like this f subscript x. We know if we plug in this point p into f partial x, we know it's going to end up being equal to 4. So we can rewrite this part as being equal to 4. So this is going to be 4 times the partial of x with respect to phi, where the partial of x with respect to phi is going to be equal to rho cosine theta cosine phi. So this is going to be times rho cosine theta cosine phi. And then you just follow that exact same logic. So this next part, if we're taking the partial derivative of f with respect to y and then plugging in this point p, that's going to give us a -3. So this will be -3. And then you do the partial derivative of y with respect to phi. So that's going to be -3 times rho sine theta. And then we're going to have cosine phi. And then the last part is the partial derivative of f with respect to z. If we plug in the point, we know this is equal to 8. So this is going to be +8. And then you multiply by the partial with respect to phi. So this is going to be times minus rho times sine phi. And so we're not completely done yet. We still haven't plugged in rho is equal to 2, and then theta is equal to pi over 4, and then phi is equal to pi over 4 into this, which I'm just going to show what the final number ends up being equal to. Right, so you still have to plug in these various numbers into rho, theta, and phi. And if you end up doing it and then adding the numbers together, it ends up giving you 1 minus 8 times the square root of 2. So when I post the solutions, I'll kind of show how you go from here to here. All I'm doing is just plugging in numbers, but for the sake of time, so we can cover more problems, I'm just going to say it ends up being equal to this number right here. Right, so this is a chain rule problem. Any questions about problem number 7? Yeah. This part. We're just taking the partial derivative of z with respect to phi. So that means we're really just taking the derivative of cosine phi because we're treating rho as a constant. And so if you do the derivative of cosine phi, it's just going to be the minus sine phi. So that's where like the minus and the sine phi show up. Does that make sense? Any other questions about 7? Okay, there might be a chain rule problem. I'm on the fence about it. But I mean, you should know how to do the chain rule. It's kind of 50-50 whether or not I put one on there. Okay, any other questions people want me to do? If I just choose one. Okay, so one kind of problem you need to know how to do, I've said this in class before, is there's definitely going to be an optimization problem on the exam where you have to find critical points and then you have to be able to determine whether or not it's like a local min, a local max, or a saddle point. And so the best problem to understand with respect to that is going to be problem 9. So I just did problem 7, then we're going to do problem 9. So you need to know how to do this. And I'm not going to choose one that's overly complicated. I just want to make sure you know how to find critical points and how to test what kind of critical point they are. So the function for this one is it tells you that f of xy is equal to x to the 4th power minus 4 times x times y, and then plus 2y squared. So it wants you to find the critical points, and then it wants you to analyze them using the second derivative test. So I need more space, so I'm going to scroll down here. And so we're looking at f of xy is equal to x to the 4th power minus 4 times x times y plus 2y squared. And so to find the critical points, you just take the partial derivatives with respect to both variables, and then you set them equal to 0, and then you want to solve for x and y. So the first thing we do is we can take the partial with respect to x. If you take the partial with respect to x, this is going to be 4 times x cubed minus 4 times y. And then we set it equal to 0. And you could kind of write y in terms of x at this point, but let's see what the second partial looks like before we do that, because maybe that will give us something easier to work with. If we do the partial with respect to y, we're going to get a minus 4x, and then we're going to get a plus 4y. So this is easier to work with, right? Because x and y are both linear, whereas in this instance, we had that x was cubed, which kind of makes things a little bit more unwieldy. So let's work with this to find a relationship between x and y. And you can quickly see we're going to find that x has to be equal to y. So if you add 4x to both sides, you get 4y is equal to 4x. You divide both sides by 4, and you'll find that y ends up being equal to x. And so once we have this restriction, once we know that y is equal to x, you can substitute in to the equation above to determine what the critical point is going to be. So if we take this equation, I'm just going to move it down. Right, so this was, I don't know a good way of conveying this. So what we're doing is we're taking this equation 4x cubed minus 4y is equal to 0. And then we can just plug in x is equal to y, and then we can solve for y, right? So this is the same thing as saying we have 4y cubed minus 4y is equal to 0. Or you can say like y is equal to x, and you can write this in terms of x. It doesn't make a difference, right? And so we can factor out a 4y from this equation. If we factor out a 4y, we get a 4y, and then we'll have a y squared minus 1, and we're setting this equal to 0. And this will tell us what our 3y values end up being, right? One y value that will work is y is equal to 0. And then the two other points that will work are y is equal to plus or minus 1, right? So we know that we have y is equal to 0 and then plus or minus 1. And then we also know that y is equal to x, right? So if y is equal to 0, we must have x is equal to 0. If y is equal to 1, x has to be equal to 1. If x is equal to minus 1, y has to be equal to minus 1. So that tells us we have 3 critical points. So the 3 critical points are the following. So the 3 critical points are just going to be 0, 0, 1, 1, and then minus 1, minus 1. And so once we've determined the critical points, we want to determine whether they correspond to local mins, maxes, or saddle points. And so this is where the second derivative test comes into play. So to do the second derivative test, you take your partial derivatives, and then you compute another partial derivative. So we need to compute the discriminant. Just as a reminder, this is what the discriminant is. So it's a function with respect to x and y. It's equal to f partial x twice times f partial y twice. and then it's subtracting, or you subtract by f partial x and then f partial y, and then you square this term. Right, so we need to find all the second order partial derivatives, and then we need to organize them in the following way. Right, so these are just polynomials, so computing the partials aren't too bad. So f double partial with respect to x is this going to be 12x squared. F partial x, and then doing partial y after, like the mixed partial derivative, is this going to be equal to -4? Right, you just take the partial derivative of this with respect to y, which is where the -4 comes into play, and then the second order partial with respect to y is this going to be equal to 4. So this one isn't too bad to compute. And so if we want to find this discriminant, we just plug in, we substitute in for the functions that we just found. It looks pretty nice here. So this implies that we have d of xy. This is going to be 4 times 12x squared. So that's going to be 48 x squared. And then when you plug in the partial here, this is going to be -4 squared. And then you subtract that, so you get a -16. Okay, and then from here, it's a matter of just plugging in the critical points and seeing what ends up happening, right? So you can see if you plug in the point 0, 0 into the discriminant, this is just going to be equal to -16. -16 is less than 0, so that means we have a saddle point. And then you can see for the other points, like they both just rely on x, right? So as long as x is non-zero, I mean, this thing is going to end up being positive. Or I shouldn't say that. I mean, x is going to be -1 or +1. If x is equal to plus or -1, this is going to be 48 minus 16. So both of those are going to be positive, right? So if you do d of 1, 1, this is going to be equal to 32, which is greater than 0. Likewise, if you do d of -1, -1, this is also going to be equal to 32, which is greater than 0. And so once you determine the discriminant is greater than 0, there's two possibilities. You can have a local min or a local max. To determine if it's a max or a min, you have to plug your numbers into the second order partial derivative, right? So now we look at the second order partial derivative. And I mean, it's kind of the same thing, right? I mean, it's squared, so the sign isn't going to matter at all. But if you plug in 1, 1 into the second order partial, this will be equal to 12, which is greater than 0. Similarly, if you plug in the critical point -1, -1, this is also going to be equal to 12, which is greater than 0. And so because the second order partial at the critical point is greater than 0, that must mean we have a local min. If it were less than 0, that means we have a local max. So this means we have local mins at the remaining two critical points. So at -1, -1, and then at 1, 1 as well. So that's the process. It might be a good idea to write down like the second derivative test. Like if it's kind of shaky when you're getting to this part, in terms of like what you need to do and what condition tells you what, can be a good idea to write down the second derivative test on like a note card or something like that. Yeah, question.
If the second derivative f of x is equal to 0, does that mean anything important?
It just means it's inconclusive. So it's kind of the worst case scenario, because then you have to use your brain. You don't want to have to do that. And it means usually you have to like draw a picture. You have to like consider level curves. So you'll plug in like sample points, but I don't plan on throwing that at you on the exam, because like those kinds of problems can take a long time, and there isn't like a set way of determining like what it's going to end up looking like. Okay, any questions about this problem? Okay, yeah, so there's definitely going to be an optimization problem on the exam. What next? Any problems in particular people want me to do next? Yeah, go ahead.
Question with the last one. If our determinant in 0 at that point, is that inclusive?
Yeah. Yeah, that could happen, like the determinant itself ends up just being equal to 0, in which case it doesn't really give you anything helpful. Yeah, any questions people want me to go through?
Number 11.
11? Which one's that? Oh yeah, I can do 11. 11's a good one. Yeah, so I probably have time to go through 11 and then one more problem. So for problem 11, it wants you to find the double integral of f of xy is equal to x cubed times y. And we're working over the region between the two curves given by y is equal to x squared and y is equal to x times 1 minus x. And so I guess the first thing I would do here is we want to determine the bounds of integration with respect to x and y. So we know with respect to y, like we know we should, like our bounds of integration for y should involve x squared and it should involve x minus or x times 1 minus x. It's just a matter of which one will go at the bottom and which one will go to the top. But we also need to determine what the bounds of integration are going to look like with respect to x as well. So to find the bounds of integration with respect to x, you just set these two equations equal to one another and then you solve, right? That's where the intersections are going to occur, and that'll determine like where the region, like where you actually have a valid bounded region between the curves. So the first thing I'm going to do is I'm going to set x squared equal to x times 1 minus x. And then I'm just going to solve for x. So x times 1 minus x, this is the same thing as x minus x squared. And then from here, what you can do is you can add x squared to both sides to get that this is going to be 2x squared. And then you can subtract, Then you can subtract this x to this side as well to get that this is going to be 2x squared minus x is equal to 0. And then from here, you can factor out an x, right? So this is going to be x times 2x, and then this will be minus 1, and this is going to be equal to 0. And so this will tell you the two x values that we're bounded between. So we know that this equation works when we have x is equal to 0. We also know it works when we have 2x minus 1 is equal to 0, which happens when x is equal to 1/2. So this implies that x is going to be equal to 0, and it's going to be equal to 1/2. So that'll give you the bounds of integration with respect to x, right? We know x is bounded between 0 and 1/2. So we can start to write out this integral. So this is x is equal to 0. This is 1/2. And then we have an integral with respect to y. And then we're integrating x cubed times y. And then this is going to be dy dx. All that's left is just determining what's going to, like, which curve is higher on the interval from 0 to 1/2. And so you can plug in a sample point. Say, like, you can plug in like x is equal to 1/4 because 1/4 is between 0 and 1/2. So if we did this, so when x is equal to 1/4, this implies that x squared would be equal to 1/4 squared, which is equal to 1/16. And if you plugged in x is equal to 1/4 into x times 1 minus x, this is going to be, so if you have x times 1 minus x, this is equal to 1/4 times 1 minus 1/4, which is equal to 3/4. So this is equal to 3/16. And so why I did this is it tells you that on the interval from 0 to 1/2, we have that x times 1 minus x is greater than x squared, right? And we're going to have that this function is larger than x squared as long as we're in this interval. And then when we pass x is equal to 1/2, it changes, right? One becomes larger than the other. And so that tells us the lower bound is going to be x squared. and then the upper bound is going to be given by x times 1 minus x. And so you should be thinking this is pretty much like doing the area between the curves. Like we did stuff similar to this in Calc 2 when we were finding the area between the curves to determine which curve is higher than the other. It's the same process, except now we're determining the bounds of the integral that we're looking at. Okay, and then from here, the integral itself is pretty routine. So if we do the integral with respect to y, first, this is going to be equal. So by the power rule, this will be 1/2, and then this is 0 to 1/2. This is going to be x cubed, and then y squared. And then we're going from x squared to x times 1 minus x dx. And so according to the notes I have right now, I'm not going to go through like the full details here, but apparently this ends up simplifying into x to the 5th power over 2 minus x to the 6th power dx. And then if you compute this integral with respect to x, I mean, this is like a Calc 1 problem now. This ends up being 1 over 5,376. Right, so the hard part is this part, like determining the bounds of integrals of the integrals, and then the other part is just doing just like Calc 1 integrals pretty much. So when I send you the solutions, I'll have more detail written out. But for the interest of time, I'm just going to write out this ends up being equal to this, which ends up being equal to this. Any questions about 11? Yeah. I guess, I mean, that could change the sign depending on what you're doing. And I guess you're still having to, like, if you're doing the absolute value, like it's like a piecewise function where you're like, you still have to kind of determine whether or not you're going to be multiplying by -1 or not. Like the absolute value of x is defined in the following way. Like to get the answer at the end of the day, like we'll still need to determine whether or not we'll multiply by -1 at the end. And so like this is when x is like greater than or equal to 0. This is when x is strictly less than 0. So I think at the end of the day, you still have to determine which curve is going to be above the other. At least that's the intuition that I have. It's like the absolute value, like you shouldn't have your final answer in terms of the absolute value. Like you have to determine whether or not it's going to be like +1 or you multiply by -1. That's what I would say. Yeah, other questions? Yeah, I thought it would be, I mean, it's just an easy number between 0 and 1/2. You can do like 1/8 if you wanted to. It doesn't matter. No matter what value you choose between 0 and 1/2, it's not going to change like which curve is above the other. So yeah, I have time to go through one more problem. Is there any problem in particular people want me to go through? Yeah. One? Oh yeah, one is one I did in the other class. Do you want me to still go over it, or I can if you want? Yeah, so one, it's kind of been a while, and we haven't really looked at this too much, so I'm probably not going to ask a problem of this nature, but I guess it's, maybe I will. I don't know. I mean, I would say it's like a 10% chance. The chances are like if I'm desperate to finish the exam, like I don't know what problem to put on, maybe I'll put on like a level curve problem. But it's still good to review. It's like these level curves, this is all the way back to section 14.1, which is like one of those ICE days we had. So there's like a video lecture. So it's been a while. So the point of level curves is to help you graph surfaces. So if you're given a function of the following form in terms of two variables, like a question could be like, how do we draw this? What is this going to end up looking like? And so in order to draw this, we set this equation equal to a constant. And so this constant c is going to correspond to some number on the z-axis, right? So effectively, we're fixing a value on the z-axis, and then we want to see what the corresponding function with respect to x and y is going to look like. And then as you continuously vary that curve, it will tell you what the surface is going to look like. So we set this equal to some constant c, and then it's just a matter of rewriting things so that way we can understand how to draw the picture. So this is e to the 4x minus y. And so I guess the hint here, like where you follow your intuition, is if we didn't have this e right now, we would know how to graph 4x minus y in terms of like, it's just the equation of a line, right? It's linear. So the first thing I'll do is find a way to get rid of the e. This can be done by taking the natural log of both sides. So this tells us that the natural log of c is equal to 4x minus y. And so this puts a restriction on what kinds of values of c that you can have, right? We have to have that c is going to be greater than 0, which makes sense because this is an exponential function and those are greater than 0. But we also know natural log is only defined for values greater than 0. And then from here, you can solve for y to find the equation of a line. So this is going to be, if you subtract 4x by both sides, you have the natural log of c minus 4x is equal to minus y. And you don't want a minus sign in front of the y, so you multiply everything by minus 1. And so you end up getting that y is equal to 4x minus the natural log of c. And so this is just the equation of a line of slope 4 that has y-intercept given by minus natural log of c, right? So when I'm asking you to describe the level curves, you can say something like this. So level curves are lines of slope 4, and then given by y and y-intercept given by minus 1 times the natural log of c. Right, so you can have something like this as your description of what it's going to look like. Right, and this is another one of those kinds of problems where, I mean, you can have examples more difficult. Like it was nice in that this was a linear function, so you can describe things easily in terms of lines. But we've seen examples in the past where we have like ellipses instead. And as you go up with respect to z, the radii ends up increasing. Any questions about one? Okay, so I'll finish class today now. And then tomorrow we have a group work where the group work is pretty much just going to be a practice exam. So it'll be 8 problems, and the problems will be pretty similar to what's on the exam pretty much. And then I also have office hours for the next hour. So if you have any other questions, I'll be in my office from 2 to 3.